Good afternoon, everyone. In the previous class, we just talked about the permutation test for the bootstrap methods, right? So we are going to talk about the Fisher's exact test here and Jackknife and the cross validation in today's lecture. So first, we just talk about the Fisher exact test. So I hope you everybody just know this one contingency table of the Fisher test. I hope you have seen that one, right? So let's consider study comparing a treatment and control or success. All right, consider treatment and control group with the binary outcomes like success and failure, and the data are summarized in a 2 by 2 contingency table that is given here. All right, so the row totals is A plus B because treatment when success is there, it is going to take the A elements and number of failures in the treatment is B, number of success in control it is C, and number of failures in control it's D. So total numbers for the treatment or the row total is A plus B and C plus D for the control and total is capital N. And for the success for both cases of both groups, treatment and control, the success is A plus C and the failure is B plus D. All right. So the row totals are fixed by the design and the columns totals are basically observed. All right. So under the null hypothesis, H naught such that there is no association or they are treatment and control both are independent. And the probability of observing such a table conditions on the margin follows a hypergeometric distribution with the probability A plus B, C A, C plus D, C, and N, C, A plus C. All right. Why it is a permutation test? Basically, under the H note, the A plus C success. All right. The A plus C success are equally likely to be any subset of the n subjects. Permuting the table labels, say treatment and control, while keeping the row and columns total fixed, lead to exactly the hypergeometric probability. So, similarly, in that case, Fisher exact test enumerates all possible tables with the given margin and the computes the p-value as the sum of the probabilities of the tables as extreme as or more extreme than the observed values. All right. For example, if I am going to take here the treatment is here and then is control, here is success, and there is your failure. So instead of A, if I'm going to take 8 and in the control it is 11 and say the failure in the treatment group is 2 and failure sorry take it 3 and failure is 7 here. So what will be the total at that time? 10, 10, that is 20 total population, 11 and 9, right? So in that one, what will be the probability of this exact table? It will be probability that 10C8 into 10C3, the success, combination of the successes, and 20C11. All right. that will be approximately, when we are going to solve it, it will approximate to 0.0321. So for a one-sided test, basically the treatment increases the successes. The sum of the probability of the tables is, with a is greater than or equals to 8, a could be 8 or 9, 10, the probability will be 0.0321, and then similarly you can get for the 9 and 10. All right. So this is the basically Fisher exact test that we use for the replication of the permutation test here. We have the R code for this one. So we just discuss the R code here. All right. So we are taking a clinical trial here where we have the drug cases and placebo cases. The success in that one, 15 cases are success and 5 cases were failure. And in placebo, 8 cases were success and 12 were failure. 12 were the failures. All right. So the code is basically, first we are going to prepare a matrix. In the table underscore data, we are going to prepare a matrix, okay, of 2 by 2, 15, 5, 8, and 12, and row wise we are going to take data. So at that time it will create the table like this only. And after that we are giving the row names and the table names, because we already have the row and tables names here, row and columns names are there. So we are going to take the row and column names. After that we are going to call the table. All right. Sorry. I think some other program was there, so that's why it creates a problem. All right. So this is your table or matrix. Then after that we are going calling the Fisher exact test here. So for the Fisher exact test, there is a direct command, that is Fisher dot test, applied on the matrix. All right, that is the inbuilt one. All right. So this is basically by default with the two-sided case with 95% of confidence interval for the odd ratio. So we just check this one, apply this, run this command. Here we are going to call the p-value, okay, of the Fisher test by the command Fisher underscore result dollar p dot value, and after a decimal up to the 4 positions we are getting the values here. This is the p-value of the model 0.0536, and after that in the next one we are calling the estimates that will provide us the conditional maximum likelihood estimates of the odd ratios here, okay, by the command Fisher underscore result dollar estimates, okay. So that is the odd ratio estimates here. And after that we are going to perform the chi-square test for the comparison. All right, because if you know that we have the chi-square test also for the this type of contingency table, we check what is the results will be there. Okay, so we just check the p-value as well as the chi-square value here. This is the p-value, that is 0.055. Earlier we had the 0.0536. So both of them almost are correct. All right. So that is your Fisher exact test for the as the application of your that one permutation test here. All right. Sorry. So the properties of the permutation test are the exact p-value. All right. So p-value is exact and under H naught, because we are going to take the sum of the observations that are less than, okay, where is the formula? That are greater than or equals to observed value plus 1 divided by b plus 1, the number of replicates. So it will give you the exact p value, right? And distribution free, so no assumption about the population distribution is needed here. And the valid for the small samples, so unlike asymptotic test, so it is also valid for the small samples. And based on the simple randomization argument, so it can be useful when you have the randomization arguments are there. That's why we call it as the randomization test. And the limitation for this model is the H naught only does not provide the confidence interval. Permutation test doesn't provide the confidence interval. If you just remember, we have not find out the confidence interval for any of the estimator. All right. And exchangeability, it requires the observation be exchangeable under the H naught. If it is not available, so we cannot go for the permutation test. And computational exact test may be infeasible for the large n. All right, so that is also one problem with the permutation test. And ties need the special handling when the data has the ties. So if the data is going to be have the ties, so at that time it may create the problem to get the exact p value. Okay, so p value will be you may face the problem to compute the p values if more ties are there. All right, because when you are computing the p value, what you are needed, you need the t star b that are greater than equals to b observed. So if it is not there, then it will be problematic. All right, so now we just go for the jackknife. Okay, so jackknife method was introduced by the Cunoli in 1949 for bias reduction. Okay, so what is the basically idea behind that, and what is the history behind that? The Maurice Cunoli, that was he was the British statistician. So he originally proposed the jackknife method to reduce the biasness of the estimators in 1949. All right, so what he did basically, he he was estimating the auto correlation of the time series data. All right, and the idea was to compute the estimator on subset of the data and then combine them these estimates to cancel the first order bias term. All right, so that was the idea of the Cunolis for the bias reduction here. Okay, and after that, Taki in 1958 give the names of as the jackknife. All right, so he what how he just give the name. He coined the term jackknife to evoke the image of the multi-purpose tool. All right, like we just say that Scott's knife or something else. So that could be used for many tasks like bias reduction, variance estimation, and other things. So Taki extended this method by introducing the concept of the pseudo values, which allows the construction of the confidence interval and the hypothesis test. All right. After that, we have the predates the bootstrap by 30 years. So basically, uh, Bradley Efron introduced the bootstrap in 1979. So that's why it is more than 30 years. All right, and jackknife is simpler and traditionally cheaper, but it is a linear approximation to the bootstrap in many cases. All right, uh, Bradley Efron introduced the bootstrap method. All right, but before him, 30 years before that, Jackknife introduced that one, Jackknife method. That was the linear approximation of the bootstrap. All right. So what is the basically key idea of this one jackknife method? The systematic leave out observations one at a time to estimate. All right. So the jackknife operates by creating n new data sets. All right. He creates n new data sets. All right. New data set of size if the original original sample size has the size of n, each obtained by the omitting a single observation. All right, for each such data set, we compute the statistics of interest like mean, variance, regression coefficient, and this yield n jackknife replicates of the estimator, that is basically theta cap I. All right, where I denotes the ith observation is omitted. This I is denoting that ith observation is omitted. All right. So the idea is to study how the estimates change when each observation is removed, hereby relieving the property of the estimator and the influence of individual data points. So how you will say it? Just take an example from your real life situation. Suppose we want to prepare a cake, or we have the recipe of a cake, and we want to check that, and or we want to understand the role of each ingredient like flour, sugar, eggs, or etc. in the that one in the cake. So what we do, we will prepare the multiple versions of the cake, and in each version of the cake we will miss out one particular ingredient. Okay, so and compare all those results, and then we check how different taste we are getting from each version of the cake. All right, so similarly in the jackknife, what we do, we just remove one observation from each sample. Okay, and we check how the estimates are going to change because of removing that particular observation. Okay, so this helps us to find out which observations are critical to the results and which gives an idea of the stability, okay, in the estimators. So that is the basic idea behind of that one jackknife method. So here bias of an estimator, right? So Cunoli's original idea, basically, original bias estimate is based on the difference between the full sample estimate theta cap and the average of the jackknife replicates. So specifically, if the bias of the theta cap is of the order of 1 upon n, all right, the jackknife can reduce to the reduce it to the order of 1 upon n square. All right. So that is basically the idea and the variance and standard error. So Taki proposed the variability, propose the using of the variability among the jackknife replicates to estimate the variance of the theta cap. So jackknife variance estimator is basically variance of theta cap of the cap of variance of theta cap is equals to n minus 1 upon n summation over the range of I goes to 1 to n theta cap I minus theta cap, sorry, theta bar cap, wait a second, theta bar cap dot whole square. All right. So here factor n minus 1 upon n is the corrects the fact that the replicates are based on the overlapping samples. All right. This estimator is the consistent for many statistics and provide the non-parametric way to obtain standard errors without assuming a specific distribution. Okay. And influence of the individual observations. As I told you, Jackknife naturally reveals that how each data point affect the estimates by giving the example of the cake. Okay, baking a cake. All right. So now, what is the mathematical way of that one uh, formulation? Is that for IID sample? Okay, for a IID sample x1, x2 up to xn, let capital T n equals to capital T x1, x2 up to xn. All right, be an estimator of a parameter theta. So the jackknife replicates will be T n minus 1 I minus 1 I equals to capital T x1, x2 up to xi minus 1 and xi plus 1 up to xn. Here we are, if you just see here, we are having xi minus 1 and xi plus 1. So what we are doing here, we are removing xith observation and then we are calculating the our estimator. All right. So the jackknife bias estimate is jackknife's bias estimates will be equals to n minus 1 into t bar n minus 1 minus t n. All right. And the bias corrected estimator is is it will be t divided by t jack equals to n into tn minus n minus 1 into t bar n minus 1. All right, that will be the corrected bias corrected estimator. All right, and the variance is, as we discussed earlier, it will be like that. All right, so now we just come here, the delete one jackknife. Delete one jackknife is basically when we have the original data x1, x2, xn, and original estimate is theta cap. All right, that is based on that one. So we are going to remove one observation only, and we are going to use the jackknife replicates here. All right. So at a time we are going to remove only one observation. All right. For example, suppose this is our data 47385. So x bar will be 5.4. So what we are going to do, we are going to replicate in such manner. We are going to remove only one value from this one every single time. So first we have 7385. So we are going to remove 4 this time. So we have the, and then we calculate the mean, that will be 7.5.75. After that we are going to remove the 7 and our sample will be 4385 and the mean at that time will be 5, and then we have 4785. So we are going to remove the 3. At that time the mean is 6, and then again we just take the sample, and this time we are going to remove 4735. So we are going to remove 8. So the mean will be 4.75. And here we are going to take the again the sample 4738, and the mean at the time is 5.50. So we remove the 5 this time. So these are the means that we are going to calculate. All right. So that is the basically delete one jackknife method. So we are going to remove one observation and we are going to calculate the sample of n minus 1 every single time. So the sample size will not change. Means if we have the sample, okay, suppose if we have the sample of size n, so every single time we just collect the sample of size n minus 1 every single time. Okay, and we will we will collect the n samples because the sample is original sample was n, so we are going to collect the n samples only. So these are the samples that we are going to collect. All right, and after that we calculate the bias or bias estimates and all these things here. So we are going to collect Jackknife's bias estimates, that is expected value of theta cap minus theta. So you already know what is the biasness is that. This is the fundamental definition of the bias. Okay, here theta cap is the estimate of the population parameter theta computed from the sample, all right, of size n, and the bias uh, quantifies as the symmetric error of the estimator. So the difference between the expected value and the true parameter value, all right, that is theta. So if biasness is positive, so that means we have the overestimation, okay, and if it is negative, it means that we have the underestimation of the theta. So now for many estimators we have the this equation, expected value of theta cap equals to theta plus a upon n plus b upon n square plus and so on. All right. For many estimators, this is an asymptotic expansion of the expectation of theta cap. It assumes that the bias can be expressed as a power series in 1 upon n, where A and B, where A, B, and others are the constants. Okay, are constants. We are assuming, and that may depends on the distribution under study but not on the sample size n. All right, such expansions holds under the regularity condition for a wide class of statistics like maximum likelihood estimates or method of moments. Okay, for the estimators, the term a upon n here, it represents the leading order bias, and b upon n square is the next term. Okay, b upon n square is the next term, and so on. So this structure is crucial for understanding why the jackknife works. So it exploits the fact that the bias is of the order 1 upon n. All right. For example, if we just take the example here, so we know that the sample variance is x square equals to 1 upon n summation over the range of xi minus x bar whole square. All right. So when estimating the population variance sigma square, okay, so we have expected value of S square is equal to n minus 1 divided by n sigma square, right? Or you can say it equals to sigma square minus sigma square upon n. So from this one, what is your A? What will be your A here? Just compare this one with this. So theta is the true parameter value, that is sigma square A upon n. So A is pure minus sigma square here. Alright, and higher terms will be 0 in this case. Plus other terms are 0. Alright, so for more complex statistics, the expansion may include the higher order terms. Alright, so that is the basically idea behind the expected value of theta cap of this expectation expansion. Alright, so now after that we have the jackknife bias estimates. So the formula of the jackknife bias estimate is that bias cap of the jackknife, that is equals to n minus 1 into theta bar dot minus theta cap. Alright. So here theta cap is the estimator computed from the full sample of size n. This theta cap is the estimator meter computed from complete data or complete sample. Not complete data, complete sample. Okay, of size n, and theta dot or theta cap minus I is the estimated computed after deleting the ith observation. Okay, theta bar dot is the estimator computed computed after removing the ith observation. Okay, and leave one out replicates by using leave one out replicates. All right, and then bias corrected estimate, that is theta cap j jack is basically n minus 1 theta bar dot minus theta cap. Okay, so the bias corrected estimator is obtained by subtracting the estimated bias from the original estimator. So in that one, how it is basically comes, so theta cap jack comes from theta cap minus n minus 1 theta bar dot minus theta cap. Okay, so when you are going to solve this one, multiply n minus 1 inside the bracket, so you will get that n theta cap minus that one minus n minus 1 theta bar dot. So that is the formula that we get after solving this one. Okay, bias minus theta cap minus bias. All right. So why does the jackknife bias correction work? So what we do, we have this one expected value of theta cap theta plus a upon n plus theta order of n raised to the power minus 2, because this is in the denominator. So when you will take the n in the numerator, so it power will be negative. So for leave one out estimates, what is there? Under the expansion of expected value of theta cap equals to theta plus a upon n, sorry, plus b upon n square and so on. Consider the expectation of a leave one out estimates based on a sample size n minus 1. Okay, because you are going to remove one observation, so what will be the sample size at that time? The sample size will be sample size after leave one out is n minus 1. So what will be your expansion at that time of expected value of theta cap? Ith observation we are going to remove, that will be theta plus a upon n minus 1 plus b upon n minus 1 whole square. Yes or no? Because sample size will remain same. All right, instead of n or n square, we will have the n minus 1 and n minus 1 square and so on. Okay, so averaging over the I, and the same holds for the theta bar dot. So now from the difference, so we will take the difference of both of them. So that is expected value of theta bar dot minus theta cap. When you will take the average of that one, all right, so it will be theta plus a upon n minus 1, and other terms we will say here order of 1 upon n square. Okay, for the large n minus 1 or n will not have the impact, so that's why we are taking n square here. All right, minus theta plus a upon n plus order of 1 upon n square. All right. So when you are going to solve this one, what it will becomes? A theta will cancel out. So you have a into 1 upon n minus 1 minus 1 upon n plus order of 1 upon n square. Right. When you are going to solve it, it will be a upon n into n minus 1 plus order of 1 upon n square. Right. So now multiply by n minus 1 both sides. So it will provide us the n minus 1 expected value of theta bar dot minus theta cap equals to a upon n plus, when you are going to multiply n minus 1 here, so it will not have the so much impact because the power will be in the increasing, so it will remain as order of 1 upon n square because this is very high order. All right, so what you will have then, but expected value of theta cap was theta cap minus theta was equals to a upon n plus order of 1 upon n square. Right. So hence n minus 1 theta bar dot minus theta has the expectation equals to the leading bias term a upon n plus some smaller order terms. All right. So it serves as the estimator of the bias of the theta cap. Right. So here what we will say. So n minus 1 theta bar dot minus theta cap has the expectation equals to the leading bias. All right. Leading bias term a upon n. All right. Plus some smaller order terms. All right. So the factor n minus 1 is chosen to cancel out the dependence on n in the leading terms. So that making the bias estimator approximately unbiased for the bias itself. All right. So that is your basically idea behind jackknife bias. Okay. So after that we have the jackknife variance. Okay. So the define the pseudo value. Okay. Pseudo value that we have defined here, that is theta curl I equals to n theta cap minus n minus 1 theta cap, leave out the ith observation. All right. This is basically Taki's definition. This is called as the Taki's definition. All right. Here, theta cap is the estimator of the complete sample, and theta cap minus I is the estimator from the sample with ith observation removed, and the sample size at that time will be n minus 1. So the pseudo value is constructed as a linear combination of the full sample estimates and the leave one out estimate. The coefficient n and minus n minus 1, okay, n minus n minus 1 are chosen so that if theta cap were an unbiased estimator of the theta, the pseudo value would also unbiased for the theta in a certain sense. All right. More generally, for the statistics with a bias of order 1 upon n, the pseudo value have the bias of order 1 upon n square here. So here the jackknife variance estimates is basically, that is your variance jack theta cap equals to n minus 1 upon n summation I goes to 1 to n theta cap minus I minus theta bar I theta bar dot whole square. All right. So this is the Taki's jackknife variance estimator. So here theta cap I is the leave one out replicates, theta bar dot is the equals to theta bar dot. This is basically dot equals to 1 upon n, because n samples we are going to collect, summation over the range of I goes to 1 to n theta cap minus I. All right. This is basically average of replicates. All right. And here we have n minus 1 upon n. N minus 1 upon n is basically the factor. All right. and it is very crucial. It scales the variability of the replicates, okay, to estimate the variance of the full sample estimator. All right, how it will work? As I told you earlier, if we have the that one, consider the simple case here. That is your theta cap is, suppose x bar is the sample mean, then what will be your theta cap minus I? It will be x bar of minus ith term. All right. And the formula will be 1 upon n minus 1 summation over the range of I goes to 1 to n minus 1. Sorry, it will be j, because I we are using here n minus 1, and here I is not equals to j xj. All right. The average of the replicates is theta bar dot equals to x bar, since each x bar I is the average of x. So the jackknife variance formula will be n minus 1 upon n, the formula of jackknife variance, summation over the range of I goes to 1 to n, x bar minus I minus x bar whole square. All right. Using the identity that x bar minus I minus x bar is equals to minus 1 upon n minus 1 xi minus x bar. So if we are going to use that one, so what we will get after putting this in this formula, n minus 1 upon n summation over the range of I goes to 1 to n, okay, minus 1 upon n minus 1 xi minus x bar. Okay, so now whole square of the entire term, right? So now just simplify this one, n minus 1 upon n into 1 upon n minus 1 whole square. Just take it outside the square term and minus sign will become the positive one. Summation over the range of I goes to 1 to n xi minus x bar whole square. All right. So n minus 1 will cancel out. So what you will have after this? You will have 1 upon n into n minus 1 summation over the range of I goes to 1 to n xi minus x bar whole square. That is, just take these terms together. Okay, so what it will be? It is s square upon n. All right. So that is the exactly usual unbiased estimator of the variance of the sample mean. This is the unbiased estimator of the variance of the sample mean. So the for the mean jackknife variance estimator is the exact and the unbiased. All right. And for general statistics, the jackknife variance estimator is consistent under the suitable smoothness condition. All right. And this one is equivalently to the variance of jack theta cap equals to 1 upon n into n minus 1 summation over the range of I goes to 1 to n theta curl I minus theta curl bar whole square. All right. This is the mean that pseudo values theta curl bar is the theta cap jack, and the bias corrected estimator is for that is basically theta cap bias corrected estimator is basically theta cap minus I equals to sorry, theta cap I minus theta bar dot equals to minus 1 upon n minus 1 theta curl I minus theta curl bar. All right. So that is your jackknife variance estimate. After that, you have the error, jackknife standard error. The standard error is simply the square root of the estimated variance. So it will be the square root of the variance of under the jackknife method of theta cap. All right. So now thing is that when it will fail, so jackknife method fails when you have the non-smooth statistics for like mean quantiles or the correlation coefficient under the certain condition. Jackknife variance estimator can be inconsistent. The reason is that the leave out one replicates do not vary smoothly. Deleting one observation can cause a discrete jump in an estimate. For example, the median may change by a finite amount, and in such cases, the replicates do not properly approximate to the sampling distribution. The bootstrap may work better, but even it can have the issue with the median. All right. And for the dependent data, second thing is that for the time series or spatial data, deleting the individual observation, destroy the dependency structure. Okay, so the block jackknife where the can be used where we just delete the blocks. All right, that can be a one solution for this one. All right. So after that we have delete D jackknife. All right, that is the solution for that one. Means this is the generalization of leave out one observation. So instead of the leaving out one observation, we will leave out the D observations at a time. All right. So this is the core idea of deleted D jackknife, also known as the generalized jackknife. So the standard delete one jackknife omits one observation at a time, yielding n replicates. However, for the certain statistics or the data structure, this may not provide a consistent variance estimate. So by deleting D observations where D lies between D is greater than equals to 1 and less than equals to n. Alright, we create the subsamples of size n minus D. Alright, this generalization allows us to tune the method to the properties of the estimator and the sample size. So number of subsets are basically NCD. Alright, the number of distinct subset of size n minus D, that is the number of ways to choose the which D observations to delete, is the binomial coefficient, that is NCD. Alright, since choosing the D to delete is equivalent to choosing the n minus D to keep. Alright, either you just delete D or you just choose n minus D, both are the same things here. Alright, in this case both of them are same, so that's why we are using n minus D is equals to nd. Alright, so this number grows rapidly with D and n. For example, if we have the n equals to 100, alright, and D is equals to 10. So what will be the samples? Alright, it will be 10C or 100C10. That is the very large value. You may say that 1.73 into 10 raised to the power 13. Okay, which is very difficult to compute. So in practice for large M, we might use a random sample of subset that we call it as the Monte Carlo jackknife, or choose D such that the number of subset is manageable. Okay. So for each subset S of size n minus d, we compute the theta cap, all right, theta cap S, that is basically T x S. Here S denotes a specific subset of indexes or indices, the observation we are going to retain, and XS here is denoting the corresponding data set, and theta cap S is the estimator computed from the that subsample. So in principle, we would compute this for the all NCD combinations. Okay, but this is rarely done for large N due to the computational restrictions. All right. So in that one, the variance of deleted D estimates, that is basically variance of d theta cap equals to n minus d divided by d into NCD summation over the range of S, whatever the subsamples we have, theta cap S minus theta bar whole square. All right, this is the variance estimator of the delete D jackknife. Okay, so here theta cap S is the estimate from the subsample S of size n minus d. Okay, theta cap S is the estimate from subsample S of size n minus d. All right, and theta bar is basically, theta bar here is 1 upon NCD summation over the range of S theta cap S, the average of all subsample estimates, average of all subsample estimates. All right, so that is your deleted D variance estimate. All right, and the square deviation measure the square of the subsample estimates here, and the scaling factor is n minus d divided by d into NCD. All right, it replaces the it is replacing n minus 1 upon n here. Okay, so why we are doing the scaling? We are scaling, it comes from the fact that the variance of theta cap S is approximately n upon n minus d times the variance of theta cap. So assuming the estimator's variance scale as the 1 upon the sample size, all right, we always take 1 upon n. So however, theta cap S are based on the overlapping samples, and these samples will be correlated. So the factor n minus d upon d accounts for the number of observation deleted and the correlation structure. For d equals to 1, this formula reduced to the delete 1 jackknife variance estimation. All right. So the common choice of that one of d is square root of n. This is the rule, or you can say the thumb rule, that balance the trade-off between the bias and the variance. If d is too small, for example, d equals to 1, the replicates are highly correlated and the variance estimator may be unstable. If d is too large, say n by 2, d equals to n by 2, if I say, so each subsample is much smaller than the full sample. So theta cap S has the large bias in compared to others, and the average theta bar may be the poor approximation of the theta cap. All right. So moreover, the number of subset becomes very unuseful at that time. All right. So trade-off, that means more stable for but computationally intensive. All right. So because of the number of subsamples, it is or we are going to take the different number of subsamples. So computationally it is very difficult most of the time. All right. So that is the problem with the jackknife bootstrap comparison. So here we have this one, jackknife for the variance, sample variance. We are taking here. Okay. We have the sample of size 2, 4, 6, 8, 10, n equals to 5. Sample variance s square equals to 10. All right. So what we are going to do, we are going to take the pseudo values, that is basically 4, 6, 8, 10. All right. And s square that we are taking here, that s square is basically, sorry, 1 upon n minus 1 summation over the range of I xi minus x bar whole square. Okay. So that we are going to take, and we are going to take the replicates for each I every single time. 4, 6, 8, 10. Okay, this is for the one sample. Removing here, and we are computing the variance for one leave out. And similarly, we are taking the all different samples, and we are computing the variance here for each one leave out. And after that, we are calculating the pseudo value. Pseudo value, how we are computing? We are computing as the n theta cap. Okay, that is theta cap is 10 here, and n is 5 minus n minus 1. Okay, theta cap removing ith value. So that is 6.67, and sample size will be n minus 1 is 4. So then pseudo value of theta I curve we are getting from here. These are the value of corresponding samples, and then we are going to find out the theta bar dot of all these one. Okay, mean of these replicates will be 10, right? And jackknife bias will be 0 here at that time, and the standard error will be approximate to 6.32. Okay, so we have the R code here for the jackknife. So we just check the R code. All right, so jackknife function of x and statistics of the statistics means we are going to define a function with the two arguments. One is the data vector x, okay, and another with the function of statistics that compute the estimator of the sample. Here we are going to take the n, that is the length of x, and then we are going to compute the theta, okay, theta hat, that will be the statistic of our given data set, right? And after that, we are going to compute the leave one out estimates. So theta underscore jack, we are going to introduce in here. We are going to apply the supply command up to 1 to n function of I, and statistics of x ith value of the x we are going to remove from the vector. So it creates the jackknife replicates for each I, and it removes the ith element and apply the statistic on that one. All right, and in the after that theta underscore bar, we are computing the mean of the replicates of all these one. All right, and after that we are going to calculate the bias. Okay, jackknife bias n minus 1 theta bar minus theta hat, and after that we are going to calculate the variance here. Okay, jackknife variance, and then we are going to calculate the standard error of the jackknife standard error, or bias corrected estimate we are going to calculate from here. And after that we are going to store all of them in the list, and we are giving the data set 2, 4, 6, 8, 10, and result in the jackknife we are going to print. Let's check this one. All right. So corrected estimate is, bias corrected estimate is 10. Standard error is 5.577. Biasness is 0. Estimate is 10. And these are the replicates mean. All right. So that is your R code for one leave out method for the that one variance. Okay. For the ratio estimate, what we are going to do, we are estimating the average cost per unit y bar upon x bar. We have the number of observations are the 6 observations that we have. Okay, and the we have the xi and yi's values is given here: 10, 15, 8, 12, 20, 11, 45, 60, 40, 52, 85, 48, and we are going to calculate the ratio. And problem with the ratio estimate is bias, so Jackknife can correct this one. So again, we have the R code for this one, and we just explain the R code. I'm going to explain the R code for that one. So here we have the X and the Y we store, and after that we are going to introduce M, that is the length of your estimate, sorry, length of your vector, and after that we are going to introduce that one. Give me a second. Um, Give me a second. Someone is there in the break in the waiting room. Okay. Give me a second. Here. I'm sorry for the disturbance. So we just again the our code. Okay. So we defined the two data vectors here, x in x and y, and the length of the data vector we just store in the uh, n. After that, we are going to calculate the ratio of this x and y. For that one, we are going to create a function. Okay, that returns the ratio of means, and r hat, in r hat we have the original ratio here. After that, we are going to apply the jackknife method. Okay, so what is the jackknife method for that one? Is basically I just explain the jackknife for the ratio. So in the jackknife, for the ratio estimator, is basically method is that if we have the ratio r cap of x bar divided by y bar, so in that one, for each six of these 6 observations, what we are going to do in the first step, for each I equals to 1 to up to 6, first we delete the pair. Okay, delete the pair xi yi, means we are going to delete the ith pair, and then we will compute the r cap minus ith, means after removing the ith pair we will calculate the x bar. Okay, what we are calculating, we are calculating the y bar divided by x bar. Sorry, it is not x bar divided by y bar, it is y bar divided by x bar. So we will calculate the y bar divided by x bar from there for minus I, and this is for minus I. Okay, and after that we calculate the R bar dot that is the be the mean of these 6 replicates. Okay, and then we calculate the bias of jackknife method. From the jackknife method, that will be n minus 1 into, sorry, R bar dot minus R cap, and then we calculate the R curve, the corrected bias estimate, that will be equals to R cap minus bias of jackknife. Okay, and then we calculate the standard error, that is of jackknife, that will be the square root of n minus 1 divided by n summation over the range of I goes to 1 to n R cap minus I minus R bar dot whole square of this term. Okay, that will be your standard error of that one. So similar thing that we are applying here in the R jack, R underscore jack, in the supply command, what we are doing, we are computing the 6 jackknife replicates by deleting one pair at a time. Okay, ratio of x. Ith value we are going to remove from the x, and ith value we are going to remove from the y. All right, and we are going to take the ratio of that one. That is the function of I. And R bar, we are going to compute the mean of the those ratios, right? And then we are going to calculate the bias with the formula that I told you right now, n minus 1 R bar minus R hat, and corrected R is will be corrected ratio will be R hat minus the bias, and the standard error will be equals to the square root of n minus 1 divided by n into sum of R jackknife minus R bar whole square. After that, we will call the original ratio, jackknife bias, corrected ratio. All right. And the jackknife standard error, we will calculate, call, and then we will find out the uh, confidence interval of the R corrected by the from the asymptotic normal method, that is R underscore corrected plus C minus 1 in minus 1.96 and 1.96 into standard error. All right, so it will be, now run the entire code. So this is your original ratio 4.342. Jackknife bias is 0.0114. Corrected ratio is 4.33, almost similar. And the jackknife standard error is 0.1107. And the 95% confidence interval is 4.1137 and 4.54. All right. So that is your jackknife method. All right. Now we will move to the further one. So when jackknife fail, I already told you when jackknife will fail. So here I just give the example for when the jackknife method is going to be fail, sensitive to the single observation, when we are going to calculate the median, and quantiles non smooth function of the order statistics, and mode for the discrete and non-continuous. So here if you just see, jackknife is unreliable here because median is changing every single time, that is 3.5, 3.5, 2.5, 2.5. So instead of using the jackknife, use the bootstrap method. All right, so what is the difference between the bootstrap and jackknife? Do you understand the are you able to determine the difference between that one, jackknife and the bootstrap method. In the jackknife, what we were doing, we were collecting the data or collecting the resampling by removing one observation or de-observations at a time, while in the bootstrap, what we were doing, we were taking the we were doing the resampling by taking from the given sample. We were not deleting any observation, specific observation from the data. We were resampling, and at that time, what was happening? One observation was repeating multiple times. All right, because it was with the replacement, right? So that is the difference between jackknife and that one. So now we will go for the introduction to the cross validation. Okay, so what is the cross validation? Cross validation is basically a resampling technique to assess how well a statistical model generalized to an independent data set. All right. So that is the basic idea of the cross validation. Okay. So now we just talk about the cross validation here. So the cross validation is a family of procedures for estimating the out of sample prediction errors, that is also known as the generalization error. It is resampling method because it involves repeatedly drawing the subsamples from the original training data set, fitting to a model on a one subset, that is called as the training fold, training fold, uh, and evaluating the performance on the remaining subsets, that is called as the validation fold. So this moves beyond the simple training and testing splits. So the resampling aspects allow us to almost for all our data for training and validation, providing a more stable and the less biased estimate of the model performance on the theoretical infinite population or further data. Formally, if we have a model f dash f cap, all right, trained on the data set, trained on data set, say capital D, we are not interested in its performance on D, all right, but in its expected performance on a new or independent observations like say X new and Y new, all right. So at that time the error will be equals to the error of L Y new comma F cap X new, all right, where L is the loss function that we similar to that one that we studied in the Bayesian, and cross validation provides a way to estimate this error. All right. So now thing is that how well will our model perform on new or unseen data? So this is the question about the bias variance trade-off. So the model selection and the model assessment. So a model with low generalization error successfully balance underfitting, that is basically the high bias, and the overfitting, that is called basically known as the high variance. So cross validation aims to provide a metric that when minimized guide us towards this optimal balance. It has an empirical way to approximate the integral over the true unknown data distribution. All right. So in that one, we have the overfitting problem. The training error decreases as the model complexity increases. All right. So basically, model complexity can be measured by the degree of freedom and the number of parameters or the uh, VC dimensions for a more complex learners. So the complexity increases the model's capacity. to fit arbitrary pattern that grows. The optimization process minimize the empirical risk, that is basically R, denoted by R empirical of f cap equals to 1 upon n summation over the range of I goes to 1 to n L yi and f cap xi. All right, which will continue to decrease the complexity. So next thing is that test error may increase. So overfitting problem may occur. So this is the manifestation of high variance. So a complex model f cap is highly sensitive to particular sample, say D, capital D, it was trained on. So if you were to draw a new training data set, say D cap, D dash, from the same population, the resampling after this one, the resulting F dash cap would be very different. All right, it would be very different. So if the expected generalization error can be decomposed as the expected value of y minus f cap of x whole square, all right, equals to irreducible error plus bias square plus variance. All right, overfitting correspond to an model with the low bias but excessively high variance. So the test error increases. The test error increasing is the empirical observation of the this rising variance component dominating the decreasing bias component. All right. So here, after that, we have the in the overfitting problem, the cross validation test estimates the test error without separate test data. So in cross validation, it is a tool for in sample estimation of out sample error. We call it as the in sample estimation. In sample estimation of out of sample error. Okay. For example, in k-fold cross validation, the data is the partitioned into k disjoint set. For fold k, we train on d minus k, all right, and the and validate on dk. At that time, the cross validation error will be cv f cap is equals to summation over the range of k equals to capital K is mod of dk summation I belongs to capital Dk L yi f cap minus k of xi. All right, this is an approximate unbiased estimate of the generalization error for the model F cap trained on the data set of size n into 1 minus 1 upon k of the size of n into 1 minus 1 upon k. All right. So this is the thing that testing yourself on the practice problem you have not seen before rather than just reviewing the solved example. So basically you look at the solved example and memorize the steps so you can perfectly reproduce the answer when you see the exact problem again. This is the basically low training error. Okay. And testing on the unseen problem, that is called as the basically the validation of the test or validation or testing. So when you see the a new problem requires that to apply the underlying principle you should have learned. If you only memorize the solved example, you will fail to solve the new problems. So this is a high validation or high testing errors. So true learning or basically the good generalization is basically true understanding allow you to solve both the seen examples and the new or unseen problem by applying the general concepts. All right. So that is the idea behind this example. So here we have the leave one out cross validation, that is called as the LOOCV method. So we have the algorithm is there. So for I equals to 1 to n, remove the ith observation from the training set, fit the model on the remaining n minus 1 observation, and predict yi on the held out observation and compute the error ei equals to yi minus yi cap, and then find out the low CV estimate of the prediction error, that will be 1 upon n summation I goes to 1 to n L y into y cap I minus I. So where is the L is the loss function. Generally we are taking the squared error loss function here, where we assume that underestimation and overestimation both are equally serious. All right. So relationship to the jackknife, loop CV uses the same leave one out structure as the jackknife method that we discussed in the beginning of this lecture. All right. So what is the idea basically here? First, we just take the I equals to 1 to n. This loop indicates the procedure that repeatedly exactly the n times where n is the sample size. Each iteration corresponds to holding out a single observation. Okay. So for large n, this becomes computationally intensive, but it provides a nearly unbiased estimate of the prediction error. Then training set. Okay. In the training set, for the ith iteration consist all the observations except the ith one. This create n different training sets for each size of n minus 1 here. These training sets are highly overlapping. They differ by only one observation. This overlap has important imp- uh, implications for the variance of the low CV estimates. All right, and then after this, we predict the fit fit the model on remaining n minus 1 observations. So our model is fitted on the reduced data set for parametric model like linear regression. This means re-estimating the coefficients for non-parametric models like nearest or neighborhoods. It involves the building the predictor based on the n minus 1 points. So the model fitted at this step is denoted by the f cap minus I. This is our model that we discussed earlier. And in the next one, predict the y cap I for the held out observation. So using the model f cap minus I, we predict the response for the held out observations xi that features the vector of observation I. So the prediction of y cap I is basically equals to f cap minus I into xi. All right. This prediction is independent in the sense that observation I was not used to fit the model, providing an unbiased assessment of the model's performance on a new observation. After that, we are calculating the error here, ei equals to yi minus y cap. So this is the row residual for the held out observation. This choice of the uh, error metric depends on the problem. For the regression squared error, that is basically yi minus y cap I whole square, or absolute error, that is yi minus y cap, the absolute difference are the common. So for classification, it might be 0, 1 loss function that we can use. So the error ei is a measure of how well the model trained without observation I predict that observation. All right. So after that, we have the low CV estimates of the prediction. So the loss function, so low CV estimates is the average of the n individual losses. Okay, here the subscript n here, that is indicates it is based on leaving out one observation at a time. This average serves as an estimate of the expected generalization error of a model fitted on a data set of size n minus 1. Because the training sets are almost full data set, so this estimate is nearly unbiased for the error of a model trained on the full n observations. Though it is slightly pessimistic, or you can say basically, as model trained on n minus 1 are typically slightly worse than applying on the data set of size n. All right, so after that, we are taking the squared error loss function that I told you. We are taking the squared error loss function that is very common in the regression. Okay, but other losses like absolute or classification error, that can also be used here, but the choice of the loss should align with the ultimate goal of the model. All right, so this is the algorithm of loop CB algorithm cross validation. So there is the mathematical detail of that one. For the linear regression, the shortcut formula is that for the ordinary least square regression, so loop CV can be computed efficiently by CVn equals to 1 upon n summation I equals to 1 to n to yi minus yi cap, that is the predicted value, 1 minus hii, where hii is the diagonal element of the hat matrix. All right. So this is the formula. Okay, shortcut computational formula. So normally LUCV would require fitting n separate regression models for each on n minus 1 observation. But for the linear regression, the leave one out residual for observation I can be expressed in the term of the full data residual yi minus yi cap, and the leverage HII without needing to refit. So this is a consequences of the Sherman-Morrison-Woodbury formula. Okay, this is based on the Sherman-Morrison and Woodbury formula, and the fact that the head matrix is the projection matrix. So the denominator 1 minus HII adjust 1 minus HII adjust the fact that the observation was used in fitting the full model effectively. All right. inverting the leverage to recover the error when the observations was excluded. All right. So this is your hat matrix. X, x dash into x inverse, inverse of x dash into x dash. All right. The matrix H maps the observed response vector y. All right. To fit the values y cap equals to hy. All right. So HII basically lies between 0 to 1. All right. Lies between 0 to 1, and the summation of HII is basically equals to P, where P is the greater potential to affect the regression fit. All right. So this is the formula for that one. Low CV for the regression, that is approximately unbiased, and high variance is there. All right. And computationally very expensive for the non-linear model. Okay. So after that, we have the k-fold cross validation. So what we are going to do, we are going to randomly divide the data into k equal sized fold. All right. So the data we are going to uh, split into k disjoint subset or folds of the equal size as possible. So randomization ensure that each fold is representative of all overall data distribution, reducing the bias. If the data has the special structure or more careful splitting may be needed to avoid that data leakage. So the choice of the k is the turning parameter on the cross validation procedure itself. So after that, for j equals to 1 to k, hold out the fold j as the validation set. All right. So in each iteration, one fold is the set aside for the validation. The remaining k minus 1 folds are combined to form the training set, and this process cycles through the all folds exactly once. All right. So a model is fitted on the training set, which contains approximately k minus 1 divided by k into n observations. So it will have the k minus 1 divided by k into n observations. For example, with k equals to 5, if k equals to 5 is there, so the training set is 0.8 into n. So model is trained exactly as it would be on the full data set using the same algorithm and the hyperparameters. So compute the prediction error on fold j. So the fitted model is used to predict the responses for all observation in the held out fold j. A loss function L is applied to the each prediction, and an average error, for example mean squared error, okay, is computed for the fold. So the formula is of that one is CVK equals to 1 upon k summation of j goes to 1 to k error j, and where error j is defined as 1 upon n summation over the range of I that belongs to the fold j L loss function of y I comma y cap I minus j. All right, where nj is the size of the fold of j. All right, so corresponding to that, we compute the cross validation. All right, so if k equals the choice of the k, if k equals to 5, good bias variance trade off means uh, each training set is 80% of the data. This introduces a slight bias. all right, but the training sets have the relatively little overlap, leading to the lower variance of the cross validation estimates compared to the loose EV. So empirical and the theoretical studies suggest that the k equals to 5 often provides a good compromise between the bias and the variance, especially for the model selection. And k equals to 10 is the most common choice. So in that one, training sets are 90% of the data and reduce the bias compared to k equals to 5 while still maintaining the lower variance than loose EV. So the computational cost is still modest for the 10 fits. Okay, so many studies has been done, and many packages in R or Python takes k equals to 10 by default. Okay, it is often considered as a safe or default balancing bias and variance computation. So k equals to n, leave one out. So in that one, setting k equals to n leads to the loose EV where each fold has a single observation. This has the lowest bias but the highest variance and computational cost. So this is the most appropriate when n is small and the model is linear, or when the almost unbiased estimate is critical and computational resources permitted. All right, so this is the k-fold one. So the visualization of the k-fold CV look like this. So remaining four are on the test. One is on the testing and other on the remaining on the training. Here in the second one, first and remaining 3, 4, 5 are on the training, and second we are going to testing. So in the same manner, we just apply the k-fold cross validation. Okay, so this is the cross validation jackknife and bootstrap connection. So in that one, CV is primarily a tool. So low CV is the connected to the cross validation in the form of the delete one. Okay, and cross validation is connected with the out of bag approximation in the out of bag way. All right, means in bootstrap sampling, the bootstrap sample typically contain the about 63.2% of the original observations, and rest are out of bag. So prediction of the out of bag observations averaged over many bootstrap samples yield to the out of bag errors estimates, which is analogous to the cross validation but the bootstrap sample training test. So for assemble methods like random forest, out of bag errors is the convenient internal cross validation, and they have the linear bootstrap, and the jackknife has the linear approximation that we already I already told you. So there is an example for the model selection in the regression. So here we have three models. Should we use linear, quadratic, or the cubic fit? Okay, so compute 10-fold CV error for each model, and model with the lowest cross validation error will be selected. All right, why not just use the training? So training error always decreases with complexity, so would always select the most complex data. So this is the R code for the k-fold selection. Okay, this is the, just give me a 5 or 10 minutes, I will complete this one. Okay, so in the next lecture we will go for the EM algorithm. So here we have the n equals to 100. X, we are generating n numbers from the uniform distribution, and y we are defining as the 3 plus 2 into x minus 0.1 into x square plus normal and 0 comma 2, that is the error, and data is data dot frame where we are going to store the values of x and y, and we are going to use the k-fold cross validation. So CV error is the function of the formula, all right, and the data, and k equals to 10. In that one, in n equals to 10, in n we are going to store the data, all right, number of observation, and in the fold we are going to create the random fold assignments for each observation. So here replicate 1 to k length dot out is equals to n, that repeats the sequence 1 to k until it reaches to the length n, and if n is not multiple of k, so some fold will have one extra observation. All right. So after that, errors we are going to store in the blank or empty numeric vector of size k. All right. After that, we are going to apply the loop. In that one, we are going to introduce the train. So in the train data, false not equals to j means select the rows whose fold index is not equals to the j as the training set. This uses the logical indexing, and in the test we are going to use the false. Okay, we select the row where the fold index is equals to j as the validation set. In the model we are going to use the linear model. Okay, that is going to provide the formula of on training the data even for the quadratic and the cubic model. So after that we have the predict. Okay, this is we are going to use to obtain the prediction of for the validation set, and the new data is the argument. Ensure the prediction are made on unseen data, and after that we are going to introduce the error. In the error we are going to take the mean of errors. Okay, here we are computing the mean square error here, and after that we are going to take the mean of that one, and then we are going to call the linear cross validation, quadratic cross validation by using these models. Okay, for linear y equals to x, for CV error for the model y equals to x plus I x square. All right, and for that one cubic x cube. All right, so now run all these. So this is the error of cross validation for the linear, this is for the quadratic, and this is for the cubic. So cubic has the minimum error, so we can select the cubic model here for our data set. All right, that we are generated from the uniform distribution and from this model. All right, so this is your quadratic uh, k-fold cross validation for the model selection, and example 2 that we have here, that is for the classification of error estimation. Okay, so this example we just take from the logistic regression for spam detection. Means our goal is to estimate the misclassification rate for a spam classifier. Means suppose we have the 1,000 emails with the features. Okay, in that one we have the word frequency, link counts. Okay, and then we are going to introduce a binary label, that is spam or harmful or not. So the model that we are going to use here, that is the logistic regression, and split it the cross validation into 10 folds. All right, and for each fold k we train the model on the other 9 folds, means 900 emails, and predict on the held out fold, means 100 emails we will predict that one, and compute the misclassification rate ek. All right, or the basically the error, and then we find out the average of those 10 error rates. All right, and the result is the estimate of the expected means classification error. So for that one the code is this. I'm going to run this particular code now. So here I'm going to take the n equals to 500. Okay, I'm going to generate the 500 observations, and the word frequency are known from the normal distribution of size n, and link count I'm going to generate from the Poisson distribution, because that will be a discrete number. Okay, and after that I'm going to each spam, means whatever the email I'm getting, that is a spam or not, I'm going to generate it from the binomial distribution, because it will be a binary number, either a spam or not. All right. So in that way it will come. So it will create the binary outcome using the logistic model with the chosen coefficients. So this is the p logics is the we are going to use for the logistic model. Okay, where word frequency coming from the normal distribution, and link counts coming from the Poisson distribution, and the spam is coming from the binomial distribution. After that, I'm going to create a data frame in the word frequency. Okay, that is my first uh, data vector. Link count is my another data vector, and each spam is my third data vector. And I'm applying the 10-fold CV for classification, that k equals to 10. So fold is in the fold, I'm going to take the sample. Okay, 1 to k. So it will randomly assign each observation to 1 to of k folds. And after that, I'm introducing the k numeric observation, a null vector or the empty vector of size k. And then inside the loop, I'm introducing the train as I introduced earlier, and testing as we introduced in the previous code. Here in the model, we are going to use the GLM, that is basically generalized linear model we use to fit the logistic regression on the training data. So this is our training data. Y is our study variable here, and word frequency and link count is our independent covariates, and data equals to train, and family equals to binomial that we are going to use. So after that, probability we are going to use, that is the predict the model. Uh, it will give us the predicted probabilities. All right. In predicted if else, probability is greater than 0.51, otherwise 0. So it converts the probability into the class prediction. If it is greater than 0.5, so it should be 1, otherwise it should be 0. Errors equals to j. So we are going to take the uh, misclassification rate for the particular fold. After the loop, we are going to calculate the mean errors, that will give the cross validation errors estimates, and the standard error divided by the square root of the k. It will give us the standard error. Now run this one. So the tenfold CV standard error is 0.296, and the standard error is 0.024. This is the cross validation error rate, that is 0.296. So that is your k fold error for 10 models. All right. For k for k equals to 10 cross validation for logistic regression. So there is a direct package for that one also, that is in the caret library. All right. This is the last one. After that, it will be finished. So caret is the library where we have the cross validation testing is there. So in the control, we have the training control, that is the method equals to CV number, how many folds we are going to take, that is 10. So it creates a control object specifying the 10-fold cross validation. After that, in the model train, the formula and the data specify the model. Okay, this is the model, and here is the data. And method we are going to introduce, that is the GLM, and the family of the dependent variable is binomial, and TR control is equals to control that will process the cross validation setting, and after that we will print the model here. Okay, so this is the RMSC squared, R squared, MAE. It is providing everything, and it is providing the summary of the sample. Okay, everything it is providing here. This is the model basically, and after that, LuCV. For that one, we have the trained control. That is the method. For that one, we are going to use the method LuCV, and model for LuCV is the train. Y follows the x plus I x square. That is basically fit the quadratic model here under the method linear model, and control equals to the control LuCV that we are introducing here. We will run this portion. Some errors are there. What is the error? Undefined column selected. Okay, means I didn't select the columns. Which columns I didn't select? Okay, I think I forgot to add something. All right. So here, okay, data. Let me check the data. Okay, data is there. So in the data, what is the Y? It is introduced as the Y or what? Okay, so I need to introduce as the Y and X, then it will work. Because I didn't introduce as the Y and X, so that's why it is not working. All right, I need to use this. Okay, so this is the Lu RMSC of the LuCV method. All right, so this is your cross validation methods are there. After that, we have the another methods that, but we are not going to discuss them. That is the repeated cross validation. That is the single K fold CV has the variance due to the random fold assignments. So solution is that repeat the cross validation multiple times with the different random splits. So in that one, repeat the K fold cross validation R times, each with the different random folds. Okay, so obtain R into K error estimates and average all estimates. So that is the basically another method. And again, after that, there is another method that is called the stratified cross validation method. In that one, random folds may have unbalanced class proportions. So in that one, stratified ensure that each fold has the approximately the same class proportions as the full data set. So in that one, we use the stratified. So data, if 100 spams are there and 900 is non-spam, so 10% spam rate is there. So stratified the 10 folds. Each fold has the 10 spam and 90 non-spam. In that manner, we need to uh, stratified. So in unstratified, it may happen that if 5 are the spam and 95 are the non-spam, so that is not good. But we need to divide in the split the folds in such manner that each fold should have the 10 spam and 90 non-spam. All right. So we use it when imbalance classification problems are there, small data sets are there, and when class proportions are very important. So at that time we use the uh, stratified cross validation method. So this was for your that one, what we call it, cross validation. And here bootstrap is finished. In the next lecture we will discuss the EM algorithm. Okay.